Okay, well, hello, and thank you for attending today's Whitmix webinar and CADIAX presentation. I'm Kirk Hilbrecht, Director of Marketing of Whitmix. This webinar will last approximately 60 minutes and is being recorded for future viewing. Those who would like a CE credit can receive 1 credit hour for each presentation. During the presentation, feel free to post any questions you may have in the webinar chat section. Our presenters will review these and answer these questions over the course of a few days, and we'll send these out to you all in response to the attendees via email. I now would like to introduce Charlene Charlie Orusa, Territory Manager for Whitmix. Charlie?
Thank you, Kurt. Good day, everyone, and guten tag to our friends in Austria and hola in Spain. So thank you guys for providing all this valuable information. And I just want to let everybody know that this is part 2 of a 2-webinar series, and you will be able to find the recordings on our website. Whitmix Corporation is the distributor for all of North America for the CADIAX and has been educating schools, military institutions, and clinical providers with the education on the features, benefits, and the utilization of the CADIAX for a number of years. Every time I've given the presentation, I always get the questions about how to apply this CADIAX data to your case and whether or not the data can be collected in the recordings can be related to any of the digital design software programs. With all those changes in the digital workflow, there's now good news about what you can do with the CADIAX data. And Christian Slavicek, he's an electrical engineer, and Thomas Haberl, software engineer, are continuing to develop the CADIAX and Gamma Dental software and its integration into those digital programs. So let's wrap it up. Christian, Thomas, thank you.
Thank you, Charlie, for this very nice introduction. Welcome everybody to the second part CADIAX webinar. First part was last week. At first, thanks to Whitmix and to all the staff members for inviting us and make this possible. I also would like to introduce again my co-worker, Thomas Haberl, Engineer Thomas Haberl. He is in Klosterneuburg in Austria, and he will be the main presenter of this webinar. Before we start, I would like to make a short review on the last previous webinar, which we did exactly 1 week ago. So here is the contents of last week. So I first talked about the principles of Condyle graphic recording, which is based on the axiopantographic principles. I highlighted the significance of hinge axis, and I think this is really important to understand that hinge axis allows us to set up in reference position a unified coordinate system, which we can mount to axis orbital reference plane to the articulator, and it is a prerequisite for instrumental analysis in the articulator and also a prerequisite for functional rehabilitation done in the articulator. The second important point is that hinge axis is significant so that we have interference-free closures. So it is, even with an anatomic face bow, you could have favorable positions of mounting, which could lead to interferences on closure, but also it protects the condyle-fossa relation in the temporomandibular joint. And thirdly, the significance of hinge axis is that we don't have curve distortions during axiopantographic recording, so we don't have wrong readings and wrong interpretations, so it's a prerequisite for accurate axiopantographic recording. Last week, I also showed a comparison of different jaw tracking systems on the market, and I pointed out the reliability of true hinge axis recording versus recordings on estimated virtual hinge axis systems. Then I talked about technical principles, recording process with the CADIAX system. As you know, we have different recording systems in the CADIAX family, product family. We have the anatomic, so the compact system, and we have kinematic hinge axis versions of the CADIAX. Then I presented the CADIAX, about the CADIAX results and the interpretations. And at the end, I also talked about calculations to the articulator, for the articulator, the settings for the articulator, the programming of the articulator, so that we can individualize the articulator regardless if it's analog or digital articulator. And I also did a preview, a short preview in how to transfer the data to digital systems. So this means into the Exocad, and this is gonna be more the contents of the second part, which will be today presented by my colleague Thomas Haberl. Please, next slide. So here you see the contents of the webinar which we're gonna present you today. At first, we're gonna talk about the indirect and direct digital workflow within the gamma systems. We have to talk about the accuracy of digital study casts, okay, because the gold standards still are alginate and silicon impressions models, and we have to look to the literature and look to see how accurate digital full arch representations are. Then we talk about gamma dental software, about the principles of the work of our software. And in detail, we also go through this CADIAS 3D, which is our instrumental analysis software. And here we have the virtual articulator with the CADIAX dynamics, integration of CBCT data, graphical numerical analysis, then of course static and dynamic occlusal protocols, so the analysis of occlusion in detail. We can measure the Condyle positions in RP and in ICP, or in centric relation and in ICP. Then we have planning tools like variation of the mandible and occlusal guidance design. And of course, there is also the transfer of the data finally to Exocad software for the further implementation in the regulation work of the cases. So this is all from my side. I would like again to welcome Thomas, and I give the word now to him, and let's enjoy what he has to tell us. Okay, Thomas, it's your floor.
Thank you very much for the introduction. Thank you for WIPMIX, to WIPMIX for organizing this webinar, and thank you all for joining. So I would like to jump right in with digital dentistry, which consists of a set of tools and workflow that allow dental professionals to operate in the virtual environment. This environment presents several advantages, including the automation of some protocols, speeding up some of the procedures, and improving collaboration. On the downside, which also have to be noted, is that we have to mention the high cost of the devices, the steep learning curve to operate them, and most importantly, actually, the common misconception of digital dentistry as a clinical concept for treating patients, which it is clearly not. It is crucial for the operator to have control over every step in the diagnostic protocol and treatment plan, to be able to still provide the patients with individualized and appropriate treatment. Here I would like to remind you that we follow the philosophy of the Vienna School of Interdisciplinary Dentistry, VISIT, which is based on Professor Rudolf Slavicek's teachings. And we at Gamma want to bring individualized functional dentistry and digital dentistry together by making sure that the digital workflows allow for the same accuracy as the analog environment, and by ensuring that the operator is permanently in control over the clinical case. So the first topic we would like to cover is how we have managed to integrate a digital workflow with the Gamma system that is suitable for virtual functional analysis. In developing our workflow, we have identified the following 4 key areas, which first of all are digital study casts, which are digital impressions of the patient's full upper and lower dental arches. And we like to call them digital study cast, not just digital cast, because they are used to study the case in the articulator, as well as for diagnosis and treatment planning. Next, we have to consider the digital maxillomandibular relationship record, meaning how we can transfer the relative position of maxilla and mandible, be it a centric relation or RP, reference position, or intercuspation from analog to digital. And in the previous webinar, we already talked about the importance of localizing the hinge axis of the TMJ. So we'll only mention it briefly here. But in summary, it is to say that an accurate hinge axis is essential for jaw tracking and for replaying or integrating the TMJ dynamics in the virtual space. The mechanical hinge axis is still the gold standard in this regard. So, and finally, we must also talk about the digital phasebow transfer, which means how can we position the models correctly in the virtual articulator with respect to the hinge axis and with respect to our reference plane, which is required in order to combine the 3D models anatomically correctly with the CADIAX recordings and other data such as CBCT. And each of these 4 areas has an inherent accuracy, or rather inaccuracy, that we need to be aware of. So together, these data form the virtual representation of the patient that will then be subjected to our virtual functional analysis. And here it is clear that only a combination of accurate data can give accurate results that match those in the real patients. So first, let's look at the topic of digital study casts. Our goal in this step is to produce suitable 3D models of the patient's dental arches that can be used to study and analyze the case. Generally, we have 2 paths for obtaining these models, which can be the indirect way or semi-digital workflow, where we take analog impressions, create analog casts, and scan them, digitize them in a laboratory scanner. On the top left, we also see the analog workflow branching off, but this is not something we will talk about in this webinar. And our second option to obtain digital models is to follow a direct or fully digital workflow. Here we use an intraoral scanner to take digital impressions directly in the patient without the need for gypsum casts. We may first take a look at the indirect digital workflow, which consists of, as just explained, taking the analog impressions, creating physical models, locating the hinge axis mechanically, ideally, and performing an electronic condylography with the CADIAX devices, registering the RP or centric relation bite with a wax plate, transferring the models, upper and lower, to the articulator using the phasebow, subsequently scanning those models in the laboratory scanner, and lastly, loading the models in the virtual articulator, where they are automatically positioned relative to hinge axis and the reference plane, provided we use a scanner that supports this operation. We've thus obtained the digital study models that we can use for diagnosis, treatment planning, and occlusal design. The accuracy of this indirect digital workflow was investigated by Dr. Uri et al. In 2020, where they compared the occlusal contacts on plaster models, analog study casts, with those on digital study casts that were scanned with a lab scanner. They found that there was a high correlation between analog and virtual contacts, better than what was recorded for the direct digital method. The indirect digital method was thus deemed reliable for virtual occlusion analysis in clinical practice. Going back to the diagram from before, let's now look at the direct digital workflow using an intraoral scanner without any analog models. Here, we go from digital impressions. We take intraoral scans for upper and lower. Again, similarly, we localize hinge axis virtually using digital phasebow and perform our jaw tracking. We still need a RP or centric relation record, which can also be taken using the intraoral scanner. We transfer the models digitally using a digital phasebow into the virtual articulator, where they can then be used or can be directly sent to the CAD/CAM system for designing and manufacturing dental restorations. And we are talking about study models. And for digital impressions specifically, there is an ISO standard in dentistry, which is 20896-1, which provides a guideline for how intraoral scanners should be tested. In this standard, they define 3 different test methods for inlay preparation, which for inlay preparation, for single crown and for full arch, and for assessing the accuracy of the full arch scan, which is the most interesting for us, they place spheres on the models, scan it, and then measure the distances between those spheres. It is, however, not specified by this standard how or if the test should be performed in vitro on gypsum casts or in vivo on real patients. The standard also does not quote any target accuracy values or minimum accuracy values that should be achieved by the scanners. However, in the following, we will see that there are some major problems with this method of testing. In our research, we tried to gather information about the accuracy of the most popular intraoral scanners. And when we contacted the manufacturers directly, only one of them responded, 3Shape in particular, who told us that they don't do accuracy tests themselves in vivo, but rather they refer or they rely on third-party universities to determine the clinical accuracy of their instrument. So it appears that the information about the scanner's accuracy is not disclosed by the manufacturers themselves, even though these scanners are medical devices used for 3D measurements. There was no accuracy stated in the technical specifications or manuals either. Therefore, we decided to search the scientific literature for answers about the clinical accuracy of intraoral scanners. And for that, we defined several search criteria to limit the findings to articles that would actually be of interest to us. In particular, we were interested in studies conducted in vivo, as we expected the scanning environment to make a big difference when it comes to salivation, humidity in the mouth, etc. We checked for full arch scans and fully dentated patient cases, as there's evidence that intraoral scanners perform best when just small areas are to be scanned, such as individual crowns or preparations. So performing full arch scans is basically the worst possible result that we would expect. Ideally, we would also like to compare against high quality and high resolution models of the same patient. And we wanted to limit ourselves to quite recent studies published in 2019 or later. This is because manufacturers release new generations of their scanners every 2 or 3 years, and conducting a proper study at the university takes a similar amount of time, meaning that by the time the study is finished, there might already be a new generation of the scanner on the market, and the study results are already obsolete. From our literature research, we screened a total of 61 articles. The first or the most important 8 of them you see listed here. The first 6 articles in this list are ones that address the measurement accuracy of intraoral scanners, whereas number 7 and 8 really helpful for understanding the challenges inherent to intraoral scanning and offer guidelines to improve the quality of the measurements. Particularly interesting was Bock et al., who in 2023, earlier this year, described an intraoral setup based on the previously mentioned ISO testing standard. So they mount metal spheres at fixed known distances in the mouth using a metal gauge that you see depicted here. And they measure the linear distances and angles between them in the scanned 3D models. However, this study aimed at checking the scanning accuracy for patients with braces, and we know that braces add structure to the teeth, which can improve the scanning quality. The results for subjects without braces might therefore be worse than what we see here. Bock found that the measured distances were true within a range of 100 to 400 microns, depending on the model of scanner used and the location of the spheres on the dental arch. For almost all scanners, the largest error was found to be between the two most posterior spheres. And this could be explained in that with full arch scans, the scanner has to stitch many small pictures together while moving from one side of the arch to the other. And all these small errors will accumulate and manifest as distortions in the 3D data. Checking just the linear distances will not tell us much about the distortions of the dental arch. So in contrast, this study by Lee and Park et al. Did not follow the ISO standard approach, but rather they overlaid the 3D models. They superimposed them. They superimposed the models that were obtained from an intraoral scanner and from a laboratory scanner, and perform the best fit surface match to bring the surfaces as close as possible together. In their results, they report an average surface area of about 100 micrometers for iTero and TRIAS 2 scanners intraoral. However, it is not clear how the model surfaces were cropped and which areas were actually used for the superimposition. And it is also necessary to understand the matching algorithm that's used to align the two 3D surfaces in detail. And it's typically not the average error that's causing most of the problems, but the maximum error. So this is also something that should have been reported. And so it seems that there is still some work to be invested and more standardized methods should be implemented for testing scanning accuracy. There are also several factors that influence the quality of the intraoral full arch scan, which are nicely summarized by two papers by Revilla Leon, also published in 2023. And these articles do not talk about the precision, the measuring accuracy in microns, but rather they provide the backgrounds of what factors are important to consider for intraoral scanning and how you can maximize the accuracy of when using your intraoral scanner. So first of all, they say that it's important to really understand the instrument that's being used, knowing the brand. Every brand is different, of course, but also the model within the brands. So there can be a difference going from 3-shaped TRIAS 4, for instance, to TRIAS 5, to the new generation, which can behave differently and requires new clinical testing. With other manufacturers, it's the same, of course. Secondly, we have to understand the scanning strategy and the level of experience of the operator that's using the scanner. Many first-time users of intraoral scanners tend to try to take a lot of pictures, scanning as much of the surface as possible, which can, however, be counterproductive, as all the small errors, the differences between the individual images, they add up. So there's no need to spend several minutes scanning a single arch, and we should use as little scanning time as possible. Of course, salivation and humidity in the mouth can also be a challenge, as well as light, influenced by the amount of mouth opening and tooth structures can be an issue. And also the number of teeth and superstructures, such as braces or other appliances, which we already mentioned, can influence the scanning outcome. More structure means more reference points for the scanner and thus a higher accuracy. So overall, intraoral scanning does not automatically solve all the problems of bad impressions, but rather it's a method that needs to be learned, that needs to be practiced to obtain good results. You have to know and understand what you're doing, and you have to test if it really fits your own clinical work. So to conclude, from our literature search, we arrived at 5 points, which is, first of all, that the recommendations of the ISO should be enhanced with suitable protocols, as currently its accuracy statements are very limited, and they should be extended with testing methods for measuring additional quality factors or metrics, such as the distortion of the full arch. Second is that guidelines should be developed to define the clinically acceptable minimum accuracies. How precise or how accurate does the scanner really need to be to have a clinical impact? Currently, there is no authority stating how accurate a scanner should be, and it's an emotional debate. It's not based on facts. The scanning accuracy is given by the manufacturer to the clinicians, who then have to decide for themselves if it's good enough for them. Thirdly, is that factors such as scanning protocol, humidity, lighting, surrounding tissues, degree of mouth opening, number of teeth can influence the outcome of the intraoral scans, and thus in vivo studies should be preferred to those made in vitro. Combining the outcomes of our literature research with the input from experienced dental professionals we spoke to, we can also conclude that particular attention should be applied when using digital impressions from intraoral scanners for full mouth reconstruction. Good quality analog casts are probably still better than what can be achieved by intraoral scanners. And finally, intraoral scanners should be properly tested for accuracy in reproducing the full dental arches, ideally by the manufacturer. And the manufacturer also should be clear about the test procedures that by which they obtained these accuracies. And they should not quote, for example, the accuracy of a single crown scan without quoting also that for the full arch. And this is likely where typically advertised accuracies in the area of 5 micrometers, for instance, are coming from. These are not applicable to full arch scans usually. So our other conclusion is that, of course, intraoral scans are a remarkable and impressive technology, but we must not be blinded by our positive emotions or the marketing of the scanner companies. Rather, we have to look at the quality of the results that we get, and we have to compare them to what we had before. These are now some in vitro tests by us to check the distortion of an intraoral scan compared to a lab scan. And we always see differences in terms of model distortion and position. Finally, we should come up with a solution that is suitable for the clinicians. Scanner manufacturers should provide adequate information and support universities in conducting studies for the clinical settings. So there's nothing worse than entering the fully digital way, only to realize that the result is not what we expected in the end. At the end. Next, the second topic is the digital maxillomandibular relationship, or the digital interocclusal record, which is mostly done by the intraoral scanner and is very straightforward. Here, the goal is to obtain the relationship of the upper and lower jaw model in reference position or centric relation. So we allocate the upper and lower jaw scans with the intraoral scanner software. We take individual scans of upper and lower jaws. And then, according to the Vienna school, we guide the mandible into reference position. We hold this position with an RP plate, or we move the patient into ICP position alternatively. And we scan the buccal surfaces of the right and left side posteriorly. This is a standard procedure in the scanning software, which will then automatically relate the upper and lower jaw scans together. And we can export these scans in this relation that we see on screen to other software. But also here it is necessary to check the accuracy of this relationship, for we can once again find a publication by Revilla-Leon, published 2023, where they compared study models or stone models with intraoral scans, measuring the distances between reference points in the upper jaw and the lower jaw, and they found differences ranging from 140 to 400 micrometers. But there are no exact reference values taken from the physical models, and basis of comparison was a laboratory scanner, which might also not be perfectly accurate. So thirdly, let's come to the digital phasebow transfer. Here we should quickly reiterate the significance of exact hinge axis. This is very important for our concept. So first of all, using a phasebow allows us to create a unified coordinate system, combine the digital models with the jaw movement recordings in a way that is anatomically correct. Basis is an anterior third of point of reference, which together with the hinge axis forms the axis orbital plane, which is here visualized as the small green triangle. And this plane is the basis for all our measurements, such as sagittal condylar inclination, occlusal plane inclination, anterior guidance, etc. So it is a prerequisite for instrumental analysis in the articulator. Also, X-ray images, CBCT data that contain just the same reference points, namely axis points and orbital point, can also be integrated into the same coordinate system. Another point of significance is that by using the exact hinge axis, we can ensure that we don't have any interferences during a closing rotation when the vertical dimension of occlusion is changed. Here, hinge axis deviations could cause different closing arcs, which are here illustrated by the different colors, and which of course can result in different static and dynamic tooth contacts. Furthermore, using exact hinge axis also protects the condyle disc fossa relationship of the TMJ from unintentional dislocation. And finally, using the exact hinge axis avoids geometric distortions of condylography curves, which could lead to wrong readings and interpretations. Here, for instance, on the right side of the recording, or on the left side on screen, we see a superimposed green protrusion curve, blue open-close curve, and we see that there's a significant difference comparing right to left side, which is caused by involuntarily or inadvertently using a wrong hinge axis during recording. So usually to mount the upper jaw model with exact hinge axis to the articulator, we use a so-called transfer stand, which relates the model to our 3 points of reference, which are the right and left hinge axis points and the orbital point as an anterior reference. These 3 points define the axis orbital reference plane. However, digital impressions themselves have no relationship to the phasebow nor to the articulator's reference coordinate system. This means that when we repeat an intraoral scan several times, the model will always be positioned differently, similar to when working with handheld models which have no fixed relation to our articulator movements. So the question is how we can relate the intraoral scans to the axis orbital plane in order to place them correctly in the virtual articulator. There are several methods already described in literature here by a study by Lin et al., where they presented or they compared different methods using average positioning, using alignment with CBCT data, or using a digital phasebow. And they achieved or they documented accuracies for these various methods ranging from 2.8 millimeters exact hinge axis to 10.3 millimeters deviation from the true hinge axis. We can also look at other methods available on the market for transferring hinge axis, but digital phase bows shown here by Zebris and Mocha, they use a virtually estimated or a calculated hinge axis, for which unfortunately there's no data available in literature describing the accuracy. On the right, we see an extension for the anatomic phase bow by SAM, which, as already mentioned, is only available for the anatomic phase bow. So again, we cannot use exact kinematic hinge axis location with these approaches. So our solution is then to develop a direct digital workflow that uses exact hinge axis. Our workflow supports all intraoral scanners, which output an open file format, such as STL, OBJ, PLY. In our example, we will show the scan with 3Shape Trios 5 scanner. And this workflow is also compatible with existing gamma phase bows and transfer stands, be they anatomic or kinematic, meaning we can support recordings that were made with CADIAX compact series of devices, as well as those with the bigger CADIAX 4 system. For our workflow, we need just one additional accessory, which is a set of 3 reference blocks, shown here. So we take the phase bow from the patient. This is now showing the condylograph phase bow, exactly adjusted to the true hinge axis of the patient. We mount this phase bow in the transfer stand. So we have brought the bite fork into a known relationship with the axis orbital plane, which is defined by the phase bow. So we can remove our anterior pointer and we insert one of the blocks that is of an appropriate height to fill in the gap between the mounting point and the bite fork itself. The remaining space we can fill with regular putty material in order to minimize the gap between the block and the bite fork. Of course, this action should not disturb the position of the bite fork itself. So once mounted, we can now proceed with scanning. And we carry out only one additional scan. So we scan the vestibular side of the block and the impressions of the upper jaw, which were taken for the full arch, which we can see here. So we carry out this scan from right to left side to obtain this 3D model here of the block together with the impressions of the upper jaw in the bite fork. But this method can also be used with the anatomic phase bow, of course. So if we use the reference AB anatomic phase bow, the procedure is exactly the same. So we would mount the block in the articulator, we mount the phase bow, and we take the scan of the block together with the bite fork. Previously, we have scanned the upper and the lower jaw separately. And we can then combine those individual scans with the scan that we took in our transfer stand or in the articulator. We can relate the upper jaw scan that was taken intraorally with the impressions that we saw on the bite fork. And we can align the block that's also included, as you can see, in our transfer stand scan. We align it to the known position of the reference block virtually. This means we have a connection from our coordinate system to our upper jaw, and we can precisely bring the upper and lower jaw intraoral scans into the virtual articulator. So we made a few trials using this method, comparing it to a lab scan, and we found accuracies of around 0.5 millimeters, which is a big improvement compared to the virtual articulation methods mentioned beforehand. Also, we see that the intraoral scans, or if we compare the trials 1 to 3 with our lab scan as reference, we see exactly the same contact pattern. So this also shows that this approach is really giving the same results that we would expect. These blocks will be made available starting in 2024, so stay tuned for that. Next, we should talk about Gamma Dental Software and Gamma Document Browser quickly. So Gamma Document Browser is our case documentation tool, which integrates CADIAX and CADIAS modules for condylography and cephalometry respectively. And it also integrates our CADIAS 3D module for digital dentistry. The whole package is then termed Gamma Dental Software, with CADIAS 3D being included since version 8.0, roughly since 2015. Gamma Document Browser, as already mentioned, includes a customizable workspace, including photo documentation, diagnostic sheet, CADIAS, CADIAX data, as well as access to our CADIAS 3D module. So we can then take the digital study casts, which we obtained either from the direct or the indirect digital workflow. We load them into CADIAS 3D. We carry out our analysis and design still in CADIAS 3D, and then we can forward this information or our planned treatment case to Exocad, for instance, to create the final design and manufacture. For the lab scan, we have to mention a few prerequisites. So we need the scanner to provide a mounting plate for gamma models. It needs to output an open file format, such as STL, PLY, object, etc. And it needs to output the data in a known coordinate system, which is consistent and always the same. Currently, we support directly scanners by Smart Optics, by Circonsan, by CADStar. All of them, I guess, are European companies, but we can also accurately and precisely import data from Exocad. So if the data is already in Exocad, it doesn't matter which articulator or which scanner was used to obtain it. So next, we should take a look at our CADIAS 3D module, which includes a number of features for virtual functional analysis. So let's jump to a quick demonstration of those features. If we start in a document browser, again, we have our photo documentation, we have CADIAS, we have CADIAX data, and here we also have CADIAS 3D. So we have already a patient case loaded. We have the two models in ICP relation in the correct position in the virtual articulator. And here in the virtual articulator, we can, of course, carry out movements based on the programming of the articulator settings. Or alternatively, we can also perform movements based on recorded CADIAX data. So we see here in the condylar coordinate systems, we see the actual movement paths that were recorded on the patient. And these are precisely related to where the model is currently positioned in space. This means we have true patient movements combined with true model positions. This dynamic data can also be used to assess the guidance pattern or the guidance system of the patient. So we can visualize the true functional guidance paths on the 3D models. We can do that for different types of movements. So we can use protrusion movements, we can use medial right, medial left movements. And if we visualize the lower jaw, maybe make it transparent, and we replay the guided movements we see. which teeth are actually dominating the guidance, where we see interferences possibly, and we can also judge the steepness of the guidance of the individual teeth, compare that with the steepness of the condylar guidance, SCI angles, to determine if there are any interferences and if there could be any pathologies related to muscle diagnosis by performing a differential diagnosis. So we can relate the findings that we see in our software to the muscle palpation or the muscle assessment that was done on the patient. Next, you see that the models here have already been segmented, meaning we can control the teeth individually. So we can determine which teeth are in contact. This procedure is currently manual tooth segmentation found in this area, but it will be automated in the next version of GTSW, which will be released early next year. And using this information, having access to the individual surfaces of the teeth, we can then also create a static occlusal protocol, meaning we have the models mounted in the articulator and we carry out a slow closing rotation. We find the first contact. Again, this can be of interest to us about how the patient would continue their movements. If, for instance, the first contact is in the posterior and the patient continues closing their jaw, we might see a distraction of the joint due to the leverage that's caused by this early posterior tooth contact. So after finding the first contact, we can continue the closing rotation until we obtain a list of contacts from first contact to last contact for each of the teeth in the upper jaw. And based on the differences or the amount of rotation that took place from one contact to the next, we can then also judge if those contacts occurred simultaneously or if there are large differences. For instance, from first contact, if it's an early first contact, we would see a large difference of rotation angle to the second contact. Another feature that we have in our software is that we can carry out simple measurements on those models. So again, we are in the correct position in the articulator. In point digitizing pane, we can place landmark points on the models. For instance, here we have digitized the individual cusp tips of the lower jaw. And based on this information, we can then create graphical analysis, such as visualizing occlusal planes, which of course will adapt based on where we place this point. And doing that, we can also check the numerical analysis to assess the angulations of the individual planes. We can judge symmetry. For instance, if we use right and left occlusal planes, we can see if there's a difference in inclination for right and left side that needs to be considered during our treatment approach. Or we can visualize other important functional descriptors such as a curve of Spee or F1, F2 guidance angles, which of course are very helpful in understanding the case and in communicating, first of all, to the patient, but also in study groups for comprehending the case by yourself. All of these values that you see here, so the numeric values, it's quite an extensive list of analysis that can be conducted using this software. These values can be taken and exported, for instance, to Excel to create scientific studies, digitizing occlusal planes over several hundred models, calculating averages. So this is also a very useful tool for scientific studies and scientific work in general. Another important feature is CPM, which means condyle position measurement, where we start off with having 2 scans of the lower jaw, one of them in RP position or in centric relation. Let's show the upper jaw to make it more obvious. And the second model here shown in blue, which is in ICP. So you can imagine when we superimpose those 2 models, we line the 2 surfaces together, since, of course, these surfaces are the same. It's the same patient and the same model. We can then observe what's happening in the joint. So here, if we would see a large discrepancy between RP and between ICP, this could mean that the patient has to work hard during bruxing. For instance, they would move from one position to the other, which can cause a strain of the TMJ and associated symptoms for muscle diagnosis or other related issues. So ideally, we would see quite similar to what we see in this patient, a small difference between RP condyle position and ICP condyle position. Next, we should talk about the planning functionalities in our software. So here we have a completely virtual and fully adjustable condyle position variator, or CPV, where we can choose to adjust the position of the upper jaw or of the lower jaw, depending on what the treatment requires. So we can numerically move the mandible to a new position here. We can control the vertical dimension, of course, by raising the incisal pin. And once we have established a therapeutic position, for instance, using this device, we can export the new model position that we see visualized in 3D here. Right-click, export, and we can directly export these files to Exocad, for instance, where they can then be used to manufacture, or to design and to manufacture a splint. So I will export both upper and lower jaw models for Exocad. And if we then switch to Exocad, this is now a prepared project definition for a splint case. So if we start the design software, we can load the scan data that we have just exported in the therapeutic position from our software. So we would load lower jaw, we load the upper jaw. We accept the current data orientation because we have exported the data in a correct way. We continue with splint design, so I will just skip this initial step. We will then see that our models, upper and lower jaw, are in the same relation that we saw in our software, now here in Exocad. So we would now be able to fill this gap that we see between the models, creating a splint that moves the model, the lower jaw, the mandible, to a therapeutic position that we've created in our software. And this position can, of course, also be defined by selecting a point on a condylography curve. Next, finally, we also have an occlusion design feature where we have virtually implemented the sequence incisal table, which, as you see in the guidances on the bottom, defines a predefined set or a sequence of guidance angles, which, going from position front to 3, 4, 5, 6, become increasingly more flat, meaning we have steep guidance angles in the front, but flat guidance angles in the back. This is following the concept of sequential occlusion, which was also established by Professor Rudolf Slavicek. And here we can adjust, of course, we can adjust the settings that are used by the incisal table, so we can see different inclinations for protrusion movements, for medial protrusion or lateral protrusion movements. And we can also adjust the posterior guidance, which we can take from either from the articulator, as it was programmed here, or we can use the actual posterior CADIAX recording that was taken from the patient, which is, of course, far more accurate than what we could do with a mechanical articulator. Here we can then also see the movements animated. And we see the cusps following our planned angles of guidance. We can then take these movements that we've planned in CADIAS 3D, and we can export as a jaw motion file to Exocad. This means if we are then in Exocad, we can, instead of using the virtual articulator, we can use the jaw movement that was defined by our software. If we load this file, put it into reference position, we can then see exactly the same movements that we saw in CADIAS 3D, now replayed in Exocad. So you see here our 3 points of reference, which are right and left hinge axis points, as well as our anterior reference point. And we can use these movements as the basis for our design for dental restorations. So this could be used to create the virtual wax-up or to design the occlusal surface of a splint even. Okay, and finally, we also have a feature to superimpose images, meaning Brux checkers, for instance, which are thin plastic foils covered by a small layer of paint that can be placed in the patient's mouth, and where we can see the actual occlusal contacts that the patient experiences during the nighttime bruxing, for instance. So they would wear this for an extended period of time, and we would then be able to include this information about true static and dynamic contacts that we see on the Brux checker in our examination. So we can take the 2D picture, put it into our 3D space, and we project it onto the surface of the 3D model. This means we can then compare this information with the static and the dynamic contacts that we saw in the static occlusal protocol or in the dynamic occlusal protocol. And those are all the features that are supported by CADIAS 3D. If we have CBCT data, which was already pre-segmented and which was aligned to the upper and lower jaw models, we can, of course, also include this data in our analysis. So if I now select here, maxilla ICP, and if I disable VTO, I can also see the mandible in ICP. And again, we can carry out the true patient movements using these files as well. Okay. So now we've covered all the features that are currently supported by CADIAS 3D and which keep being expanded with each version of the software as it's being released. For more information, we would like to refer you to our homepage or our product catalog, which you can download using this QR code. Here's a link that you can simply scan on your smartphone, and you can download the catalog in PDF format and read about the features. And with that, I would thank you very much for your attention. Again, I would like to thank WebMix for the invitation to host this webinar. And we'll look forward to your contacts. Thank you very much.
Thank you very much, Thomas. That was a great presentation. I love the way you merged everything in that Gamma Dental document browser. And I'm hoping that all of our participants appreciated the merging of the files and being able to design in the design software with that information. So with that in mind, I hope we got a rich database of questions coming at you next week. And we'll look forward to getting that and posting it on our website along with the rest of the other webinar. And you'll be able to view them from there. Let us know if we can help. And thank you very much.
I would be happy to help. Thank you very much.
Thank you. And thank you everyone for joining us. And you can contact myself or Ravage Strizny for any demos or information that you have about the CADIAX. Thank you.